Hello everyone. In this video we're going to talk about cumulative density function, or CDF. And this is specifically for continuous random variables. And cumulative density function, the key word here is cumulative, and you will see why. It's very similar to CDF function for discrete random variables, but here is for continuous. So it's an alternative method to describe distribution of continuous random variables, and the definition, as you can see, is probability of x less than equal to x. So it's accumulating all the probabilities until point x. How do we calculate that? Well, if you're calculating the CDF for point x, you're integrating to point x. From where? From negative infinity, or the beginning point of the range of that random variable. And you're integrating on the PDF function. So you're integrating the PDF function from the beginning of the range to point x. And that will give you the CDF function. The CDF function, we showed it with capital F instead of small f, where we're indicating the PDF function. So I want to point out again that if you are given a PDF function and you want to find the CDF function, you're integrating from the beginning point of the range to x, and that is very important because you want to have a function at the end that has an x in it, so you don't integrate from the beginning point to the ending point. If you do that, that is equal to 1, but you integrate from the beginning point to x. So when you think about the CDF function at point infinity, or the ending point of the range, is equal to 1, and at the beginning is equal to 0. Because at the beginning you haven't accumulated any probability, so that's 0, and at the end you've accumulated all the probabilities, so that's why it's equal to 1. So that's why all the CDF function has this increasing trend, because you're accumulating probabilities. So you're looking at this CDF function here. Can you think of the PDF function that is associated with this CDF function? Okay, I want you to think about this. Pause the video and draw a PDF function for this CDF function here. So because this slope of increasing and the CDF function is constant slope, you can guess that your PDF function is in a straight line, or a uniform function. Basically, from 0 to the same 20 range of this random variable, your PDF function looks like a straight line. And when you're integrating on this function, it becomes increasing from 0 to 20. At point 20, it gets to 1. Here, the PDF function, we have 1 over 20 here, so that the area under this curve is equal to 1, or 100%. So the area under that entire curve is equal to 1, so as this ending point of the CDF function ends at 1. So if you want to calculate probability of, let's say, x between 5 and 15, if you were going to use the PDF function, you would have to calculate this area by integrating on the PDF function from 5 to 15. But if you have the CDF function, what you can do is, this point here is called cap f of 5. This point here, right, because this is 5 and this is 15, and this is cap f of 15. So you can get these two values and subtract from each other. It will be the same as calculating this area. And that's why here we're saying if you're calculating probability of x between A and B, just calculate the CDF at point B minus the CDF at point A, and that would be your answer. If you happen to have that function, CDF function, just plug in B and A in there and get the CDF value. And here you can see the relationship between PDF and CDF function. So let's take a look at one example to make this a little more clear. It says reconsider example 3.1, where we have this function, this PDF function, and let x denote the magnitude of a force applied to a steel beam measured in Newton. And the probability distribution of x is such that its PDF function is this. It's a uniform function between 300 and 700. And we want to derive the cumulative distribution function first. So to derive the CDF using the PDF function, we would have to integrate from the beginning point of the range to x. So let's go ahead and do that here. So part A, we're integrating from the beginning, which is 300, to x over 0.0025 d of x. And that is equal to 0.0025 x. Here from x to 300, so we're replacing x with x and then with 300, and we're subtracting, so 0.0025x minus 0.0025 times 300. Okay, so this is not x, this is just indicating multiplication here. So when you do that, you'll get this function of 0.0025x minus 0.75. And that right there is your CDF function, which you call it f of x at point x, basically. Now that you have the CDF function, find the probability that the force applied to BIM is less than 500 Newton. Well, for part B, you can clearly see that probability of x less than 500 is asked. And what you can do, based on what we talked about here, you can do f of x at point 500. And that would be 0.0025 times 500 minus 0.75, and that is equal to 0.5 or 50%. That's the probability that the force applied is less than 500 Newton, about 50% chance. Now, part C of this problem says find the probability that the force applied to the BIM is less than or equal to 450, but greater than or equal to 375. So we can use the same logic that we used here for part C as well. And that would be probability that x is between 450 and 375 would be f of x at point 450 minus f of x at 0.375, and that's exactly what we say here in the same example that I talked about for 5 and 15 on this graph. And here this would be 0.0025 times 450 minus 300 minus 0.0025 times 375 minus 300. That will be equal to 0.375 minus 0.1857, which is equal to 0.1875.